So we're going to take a look at Chapter 8, and Chapter 8 is all about integration and different integration techniques and looking at how we can work out these integral problems using a lot of different styles and techniques. So this first section, 8.1, really isn't anything new. It's just kind of looking at a lot of the rules we've already done, mostly U substitution and integrating with the inverse trig functions to kind of get a sense of what kind of things we want to look for. So this first example, it just says compare each of these integrals. So they all look really similar, but the techniques we would use to approach each one are slightly different. So look at the first one, look at the second one, look at the third one, and kind of think about what the difference is and how you would approach each problem. The first one, hopefully you recognize. Now, of course, the 4 is a constant multiple, so that could go to the front. That's not a big deal. But if you have 1 over x squared plus 9, hopefully you recognize that that is in the form for the arctangent, where a is 3 and x, of course, is the variable. So we would just have 1/3, because remember arctangent takes the 1 over a, so 1/3 arctan of x over 3. So very straightforward, nothing tricky, no U substitution involved or anything like that. Now look at letter B and tell me what the difference is. This does not fit arctan because the problem is you have this x up here. So the alternative then would be to use a U substitution and let U equal the denominator, x squared plus 9. And then, of course, the derivative would be 2x, divide by 2, put the 1/2 in the front, and we have 1 over U du is the substitution. And so our result is a natural log. And so what's different about letter C? Well, we've got this x squared on top of the x squared plus 9. When the degrees are the same like this or it's top heavy, a lot of times a good strategy to use is to simplify this in some way using long division. And we can go over this more in person, so the long division may not be real obvious right now where I'm getting this from, so remind me, let's go over this again in the office. But the idea is that it's not a straightforward U substitution like the last one was, because you've got x squared in the top and the bottom. And like I said, we'll go over this one again in the office. Remind me to do that. But I want you to notice that it's not just a U substitution like the last one was, and it doesn't directly fit the arctan rule. All right, how about this one? We've got the integral of x plus 3 over the square root of 4 minus x squared. So hopefully the radical in the denominator of a squared minus x squared is jumping out at you as looking like the arcsine rule. What I think might be helpful here is to split the numerator. Remember, we can always split numerators. So we've got x over the radical as one integrand plus 3 over the radical as another integrand. And of course, the 3 is a constant multiple. The second one is the arcsine rule. Directly, a is 4, nothing tricky here. The first one requires a U substitution because we've got the x on top and we've got an x squared in the denominator. So if we let U equal the 4 minus x squared, the derivative, of course, will be negative 2x. So if we bring the negative 1/2 to the front, we've got the integral of 1 over the square root of U, which of course is U to the 1/2. This is a power rule. We can think of it as U to the negative 1/2 and use our power rule. And I didn't finish the first integral, which was what I was looking for. If this first integral, if we use a power rule and simplify it, this is the result we would get. The second rule, though, like I said, you see that that's an arcsine where a is 2. Remember, arcsine does not take the 1 over a in front. So that becomes 3 times the arcsine of x over 2. How about this one? We've got x squared over the square root of 16 minus x to the 6th. Again, this kind of looks like it might fit the arcsine rule. We've got the radical and we've got something squared minus something else that's squared. Notice that x to the 6th can be expressed as x cubed squared. So this will actually fit the arcsine rule if we do a U substitution and we let U equal x cubed, because the derivative of x cubed will match up with the x squared that we have in the numerator. So we're going to have a 1/3 in the front because the derivative there is 3x squared. So we've got 1/3 times the integral of 1 over the square root. And I put the 16 as 4 squared just for emphasis, but a is 4 minus U squared du. So that gives me 1/3 times the arcsine of u over 4, and then remember to replace the u with x cubed. We've got the integral of 1 over 1 plus e to the x. So at first glance, this doesn't look like anything that we can do so far. We don't have a u substitution, I don't think, because of the e to the x. That's kind of messing us up, and we just have a 1 on the top. It doesn't look like any of the inverse trig rules. Maybe an arctan because I don't have a radical, but this one's going to require something that's a little bit different. We're going to do a u substitution, and we're going to let u equal that denominator. The derivative, of course, would be e to the x dx. And then what I'm going to do is I'm going to solve. I'm going to do an extra substitution here. And what I did in the top, so this is not very intuitive at all, and we can go over this again in person, but what I did in the top, because I need this e to the x to be part of the integrand to make this u substitution work, in the numerator I added e to the x and I subtracted e to the x. Of course, that's just like 0, adding 0, right? So then what I'm going to do is I'm going to split this into two integrals. So 1 plus e to the x over the denominator is one integrand, and then e to the x over the denominator is the other integrand. This first integrand just turns into 1, so that's the integral of 1. The second integrand now is in the format I need to make this u substitution. If we let u equal that 1 plus e to the x, the derivative needs to contain an e to the x, which we have in the numerator, so that becomes 1 over u du. So now we're going to integrate, and I want you to also notice too, this first integral is still in terms of x. This did not involve the u substitution at all. So the integral of 1 with respect to x, of course, is x. This other integral is a u substitution. So the integral of 1 over u with respect to u would be the natural log of u, and then replace the u with what we substituted earlier, the 1 plus e to the x. Okay, this one we've got the cotangent of x times the natural log of sine x. So I'm going to try a u substitution. I'm going to let u equal the natural log of sine x. So the derivative of that would require a chain rule, right? The derivative of the outer function, the natural log, but evaluated at the inner function, the sine x, times the cosine of x, which is the derivative of the inner function. That, of course, is cosine x dx, which is equal to cotangent x, and that's what we need. So we have the integral of just u du, because the du turned into cotangent x dx. And so we have u squared over 2 plus c, which is the natural log of sine x quantity squared all over 2. Okay, the integral of tangent squared of 2x. Let's deal with the 2x first. So I'm going to do a little kind of a mini u substitution here. I'm going to let u equal 2x. The derivative, of course, would be 2, so that means I'm going to have a 1/2 in the front, and this just becomes tan squared of u du. This is actually a trig identity. You may or may not remember, but tan squared is equal to, it's one of our Pythagorean identities, tan squared is equal to secant squared, and so it's tan squared u, secant squared u minus 1. This we can integrate. We can integrate secant squared. That's one of our integrals from Calc 1. That's just tangent of u. And then, of course, 1 with respect to u would be u for the antiderivative. They both take the 1/2. Go back and make your substitution for u. U was 2x. Notice this u, if we replace it with 2x, the 2 in the denominator cancels and just leaves us with x. So kind of some general strategies here you want to look for as we go throughout this unit. Expand or multiply out the numerator if that's helpful. Separate numerators into different fractions and set up two different integrands. That might be helpful. We saw that in a couple of these examples. Complete the square. That tends to work better when we have a denominator and we need to make it fit one of our inverse trig rules, and we'll talk about that some more. Divide using long division, if that helps. Add and subtract terms like I did with that e to the x a couple minutes ago. Use trig identities like we saw in that last example. And then another strategy that may come up from time to time is to multiply the numerator and denominator by the conjugate of something. We'll see some of those when we work some of the problems in section 8.1.